Okay, so today basically what we're talking about, we've actually been doing this throughout the semester. Most of the skills I'm about to cover right now really are not anything new. But before I get into the actual calculus, what I'd like to talk to you about is the general relationship graphically and logically between cost, revenue, and profit. So let me see here. Let's start off with that. Okay, and we've talked a little bit about this before in the past. Hang on a second. Okay. All right, so our revenue function would look something, our cost function, I'm going to start with that. Before you do any business, you start off with a fixed cost. So you have expenses that have nothing to do with the quantity that you're producing. Actually, I'm going to put that in black. So my x-axis is going to be my quantity, and my y-axis is going to be money, measured in dollars. So whenever I begin doing business, automatically I start off with costs. And as I produce more and more things, my cost begins to go up. But as we start producing more and more things, my cost becomes more and more efficient. In other words, I get what's called economy of scales. And basically, if I have a factory, let's say I'm Tesla for just a moment, if I'm producing 10 cars, my cost per vehicle is going to be very, very large in that factory. If I'm pumping out 1,000 vehicles a week, my cost per vehicle goes down greatly because of that. My costs are still going up because the material needs to go into building the Tesla, but all that factory. So basically, my function kind of looks like a little bit of an S, and then it shoots back up. And we begin to lose efficiency. So this isn't really a huge important point, but this point somewhere around here, actually, no, it wouldn't be. Technically, when we talked about average cost per unit before, graphically, if I talked about the average cost per unit, uh, it generally occurs when I connect this line parallel and touching a tangent that goes through 0, 0. So this is graphically how I can find the lowest average cost per unit. Now, again, not a big issue per se for what we're doing, just kind of talking about in general. Revenue, on the other hand, tends to look like this. If you sell nothing, you make exactly nothing. So that's a pretty straightforward figure, 0, 0. And basically, as the quantity changes, you will see a revenue function that really tends to look generally standard like a parabola. And I'll tell you why, because I need to keep lowering the price to get more and more units out that door. If I keep lowering the price, eventually the price reduction is going to have more impact than how many more units I get. So eventually, my price is going to be so low that my revenue actually would zero. I'd have to actually give it away for free, which then, sure, people would take a lot, but my revenue would be zero. And last but not least, so let me label this. This is your cost function. This is your revenue function and your profit function. So from here, I can create a profit function. Let me zoom in here a little bit. Oh, come on over. All right. So what I'm looking at for profit is this amount of fixed cost here is going to be how much money it takes me before when I sold zero, that's going to be my loss, that exact amount. This here is called the break-even point. That is when my cost and revenue are exactly equal. So for that quantity, my profit. So what I'm saying is at that quantity, the amount of money that went out of my pocket is exactly the same amount of money that went into my pocket. Revenue and cost are equal at this amount. What's interesting is over here is another break-even point. And once again, at this quantity, whatever that quantity is, my costs and my revenue are exactly the same for that quantity, and I make nothing. What's interesting is my little sweet spot in between here, where my revenue is bigger than my cost. That's where you're making money. So when I graph that, my profit function basically looks like this, where somewhere in between here, I'm going to find our maximum profit. So these are basically all economic equations that you need to kind of get comfortable with. So I like to just keep going over them because you're going to see them over and over and over in many other classes. So just kind of getting a good grasp of what's happening here in general. Now, so depending on what our goal is, and this is important, I may want to look at minimizing different equations for different purposes. So hang on, let me see. I'm gonna hang on 1 second. So for instance, I'm just going to work a couple of examples out of the book to start with that are important. All right. So looking at this example. So in this situation, my goal is to, uh, let's see, got a cost function. We want to find the cost, average cost, and marginal cost of producing 1,000 items, 2,000 items, and 3,000 items. Okay, so let's talk about those three different functions. The cost function, we have that right here. Marginal cost is the next easiest thing to come up with. And I'm going to come up with that by taking the derivative of my cost function. So the derivative of this function, c prime of q, is 2 plus 0.002q. And again, I'm doing power function. The derivative of constant is 0. The derivative of 2q is 2. Multiply the exponent and subtract 1 from the exponent. So that is your marginal cost. It's just a derivative. And average cost. So, average cost, you have to have that formula well memorized. Average cost, I'm just going to put it AC for average cost, is equal to your cost divided by your quantity. So total cost divided by quantity. So for that, we're going to get, let's see, this over a little bit. I can write it either this way, 2600 plus 2q plus 0.001 q squared all over q, or I can rewrite this as individual power functions such as 2600 q to the negative 1 plus 2 plus 0.001 q. So I just divided that through term by term by term. So with that, finding the output by plugging in 1,000, 2,000, and 3,000 each of these formulas, it's not too challenging whatsoever once you have the formula. I'm not going to plug it into all of them. I'm just going to plug it in to, let's just say, our average cost function. So once I have this, nice thing is whether you're using Desmos or a calculator, if I'm using my calculator, I'm probably going to take my X value, 1,000, store it as X, enter, and then plug in my equation exactly as I'm seeing it, 2,600. Let's see, I could either do X to the negative 1 or just divided by X, might be easier for plugging in, plus 2 plus 0.001 X. So that is my average cost per unit when I have, let's see, hang on. Come on, calculator. There we go. So $5.60 is my cost per unit, and that's in dollars. Yes, just double checking my units for producing 1,000 units. If I wanted to change that to 2,000, again, once you have it in your calculator, I can just store that as X, enter, second function entry, second function entry. I don't have to retype everything. And we can see that my average cost per unit is $5.30 when making 2,000 units. So again, just a matter of getting the formulas first and plugging and chugging from here. So my second part of my question is, at what production level will the average cost be the lowest? Average cost, that's important. So I'm focusing on my average cost function, and I want to minimize the average cost function. So anytime you're asked to minimize a function, that's the key here, optimization. What I want to do is take its derivative and set it equal to 0. So I will do that for the average cost. So my average cost function's derivative equals negative 2,600 q to the negative 2 plus 0.001. So again, I'm just taking the derivative of this term by term. I'm going to take that derivative, set it equal to 0, and once I do that, I can solve for q. So probably the easiest thing at this point would be I'm going to move this term over here and get rid of the negative exponent all at one shot. So that gives me 2,600 over q squared. I'm now going, that's kind of an ugly looking q. I'm going to move my q squared over by multiplication. Going to divide both sides by 0.01. 600 divided by 0.001. And I'm going to get a very large number, and then I'm going to take the square root of that number, second function square root. Technically speaking, I should have a positive and negative possibility. However, it's not possible to make a production run that is negative. So even though algebra says a negative will work, our current dimensions do not allow for negative objects. So that's not a possibility. Q is going to be approximately, what do we got here, 1,612. And let's see. At what production level? So that's the production level. 1,612 if I round it to the nearest unit. Okay. So again, we're not doing anything that we haven't been practicing so far. We're still doing the basics, taking my derivative, setting it to zero many times is going to either produce the maximum or minimum on a continuous function. So that's what we're looking at. Now, so that's one of the things we're going to be looking at today. Let's see, I had that and that. Okay, so next thing I want to talk to you about is elasticity. Okay, so hang on just one second. With this, elasticity is an economics formula. And anytime you're dealing with an economics formula, it's basically designed by economists to help an economist come up with a solution and a system. So basically, what you want to do is make sure that you know the definition of what elasticity of demand is. So here's our definition. And basically, what you're doing is looking at the relative price to quantity. So when I say relative price to quantity, that's this. So price to quantity divided by the derivative of the price function with respect to quantity. Now, that is my basic formula that they're given. We're going to change it up just a little bit as you notice. So price on top, and this is the price as the demand function of quantity. So it's the same thing. Quantity on bottom of my fraction, quantity is still on the bottom of my fraction. So this is compound fractions, and rewriting this versus this are two different ways of writing the same derivative. One's writing it as a derivative function, and one's writing it in individual partial derivatives, changing y over changing x format. So it's just different notation, but saying the exact same thing. So we've got a formula. Some things we need to know about that formula that economists tell us. So what does elastic mean? And this is important. So we talk about elastic and inelastic and unit elastic. So basically, if this function, the elasticity function, is larger than 1, we say it is elastic, which means if we increase the prices, let's see, revenue increases if prices are lowered. Increase in demand. So what you're saying here is whenever this function is bigger than 1, if you lower your prices, demand will go up enough that you'll make more revenue. That's elastic. Again, if I lower my prices, the demand will go up so significantly that my revenue will go up. Inelastic says the exact opposite. That says, hang on a second. That says if my prices is increased, my demand will go down enough that my revenue will go down. So I lower my price and my revenue goes down because of a decreasing demand. Okay, so increasing prices decreases demand. So, and unit elasticity, when my elasticity function equals 1, my revenue is maximized. So with this information, we're going to attack example number 5. So we're given a demand function. The very first thing I'm going to do is come up with the elasticity function. So I got it equals negative demand function, which I am given right here. So I'm going to place that in there. 75 e to the negative 0.05 q. That's my demand function. Quantity is just q. We don't do anything with that. And the next thing I need is the derivative of that demand function with respect to quantity. So I'm going to take my demand function and I'm going to find its derivative. So looking at this, the derivative of this is, so the derivative of any exponential function is basically itself times its rate. So the rate of this is negative 0.05, and then I'm just going to multiply it by the original function. Now, I'm not going to simplify this one, and I'm going to show you why I don't want to simplify this one particular one. Because when I plug it in, so now I got that, I'm going to plug it in right here. Notice what I have, negative 0.05 times 75 e to the negative 0.05 q. This function reduces down a lot. So final answer, put that in black. So I got a negative over negative, so it's positive. This reduces with this. So basically I have what? 1 and the signs are both now positive, negative divided by negative. And I have 1 divided by 0.05, which gives me 20 over that q. And that is my elasticity function for this particular situation. Now, we want to maximize the revenue, and we know that happens here. So basically, all I need to do is set this equal to 1, solve for Q, and we get that revenue is going to be maximized when Q is 20. And let's see, write a formula and determine elasticity of demand E and determine the price and unit that maximizes revenue. So we've got the unit Q. Now we need to figure out the price, okay? And we have that price function because that's what this function here is. This is my actual price. So I've got that. I've got Q equals 20, which means, move this over. Q is 20 and price is 75 e to the negative 0.05 q, and q is 20. Okay. And let me just check my units here before I speak, because those are important. Okay. So my price, I'm going to assume, is in dollars, and my K is in units of production. Meaning, I'm going to maximize my revenue with a price of, what is that, 27.59? Oops. 27.59. When my price is 27.59, I will have, and a quantity of 20 will maximize my uh, price. I mean, my revenue from all of this. Okay, it's a little weird, but again, that's all we're doing with this situation is running through this process. Now, let me see, hang on a second. Da-da-da. I'm going to do one more situation like this. And if you give me just a second, we're going to change our conditions, but not our method. So might be a tad bit more challenging. I'm going to get rid of that one and let's put in a different situation here. Hang on just one second. Oops. Hang on. Hang on 1 second. Okay. There we go. So again, what's really important to recognize in this situation is that price is your demand as a function of quantity. So even though I'm writing it as just P here, it's still the demand function. So my elasticity function that I'm going to write is going to equal this with a negative 155 minus 0.035 Q all over. So that was that top part here. My quantity Q is still just Q. And last but not least, I need the derivative of the price function. So to find the derivative of the price function, which notice, because I wrote it in terms of P here, I can write this dP over dQ. Again, it's different notation, but it says the same thing. That's really important to be able to recognize those different forms of notation. And that simply equals negative 0.035. Now, this one does not reduce nicely, so, well, as easily. So what we're going to do is reduce it piece by piece. So first piece, what do I mean piece by piece? I'm going to split my numerator into two pieces, two terms, front term, back term. And I'm going to take each one of those and divide it by my denominator. So the first one is negative 155 divided by, let's see, negative 155 divided by that negative 0.035. And let's see if I can write that as a fraction any better. Probably don't have to, but it might just be nicer in the short run if it comes up to a nice clean fraction. It does not. So I'll round it to the Uh, oh, probably round it to the hundredth place to start with. 4428.57, I believe. Yes, Q to the -1. The second one, actually, that reduces perfectly to 1. This comes from my first piece. That +1 comes from taking the top, that -0.035Q, and dividing it by the denominator, which you should notice is exactly identical. So this is my elasticity function, and I know that revenue is maximized when this equals 1. And that's what we're looking for. Yes? Let's see. Okay, I didn't do part A. That's just plug and chug. Plug 65 into the formula P and solve for Q. So compute the elasticity of demand when the sunglasses are priced at 65. Okay, so let's do that. So now the question is, what is elasticity when the sunglasses are priced at 65? Okay, got it. Okay, so what do I need to answer that? I just need to be able to plug the correct amount into my elasticity function. So the question is, what is Q when P is 65? Then I can plug it in, yes? So that's part A. And I do that pretty straightforward. I take that formula, let's color code this, plug in 65 for P. 65 equals 155 minus 0.035Q. And I'm going to solve for Q. Now I'm going to do this all in my calculator. I'm going to take that 65 and I'm going to subtract the 155 from both sides. Now it's over there with the 65, and I'm going to divide both sides by negative 0.035 to solve for Q. And I get 2571 is my quantity. I'm going to write that down. And 0.43 we'll say for right now, approximately. Oops. There we go. Okay, so we're going to now calculate the elasticity by using this function for this quantity. So here we go. We've got, I'm actually going to store this as X because I'm lazy. That way I don't have to type it in. And then I have 4428.57. And I have it times Q to the -1 or simply divided by Q. In this case, divided by X plus 1. So what does this tell me? This tells me that revenue will increase if prices are lowered, and the demand will increase. That's my interpretation. So again, let's talk about how I'm making that interpretation. I've got a output that's bigger than 1. So I'm going to read you the answer. My demand is elastic because my elasticity is 2.722 telling me that my revenue will increase if prices are lowered, causing an increase in demand. So I don't have to figure this out. I just have to put the pieces together like a puzzle properly. That's the trick. Know where your puzzle pieces are. So if I was doing demand situation, I would have that definition and that table up as I'm working the problem every single time. It makes everything just a lot more straightforward and how it's going to flow. So I'm just each time, it's just appropriate use of the information. And that's a lot of times with word problems. Students are always like, "Can you give me an example?" Of certain situations, yes, but there's infinite number of word problems. It's not really so much about learning new math, it's just being able to apply the given formulas that you have been presented properly. So, with that, does anyone have any questions about dealing with elasticity? Which, again, the other stuff, taking the derivative, set it equal to zero, you've seen that multiple times already for optimization. So, everything else is just doing that over and over and over again. Elasticity is only the new, unique way of optimizing revenue that is being introduced in this section. Everyone seemed to be fairly comfortable and happy with this. Okay, so I'm going to hang on just one second.